I will be punctual with this video because I think we're missing a lot of our friends in this class today. I don't know, like when I woke up, I was like, okay, it's a little bit snow. And then when I got in my car to come here, it was a lot of snow. And traffic wasn't moving on 5th South or University, so. Okay, so we have covered material balances, thermodynamics for phase transition. This section is still, I guess, kind of a thermodynamics class, but you could also argue that material balances are also part of the thermodynamics, right? So energy balances are all about simplifying this equation. The change in internal energy as a function of time for a system. If it's a closed system and nothing changes over time, then it's a very boring system, right? So if it's a closed system that changes over time, we would integrate this, and the solution to the integral would be U2 minus U1, right? What's the final internal energy minus the initial internal energy? We are mostly concerned about open and steady state, so that's why we look at mass flow rate times by the specific enthalpy for all of the streams coming in minus the summation of the mass flow rate specific enthalpy for all of the streams leaving. We can have heat coming in. Now we normally write Q as just one, but you could have multiple heat streams coming in and out, right? Plus work minus P dV dt. So question, how do we know, or how do we model what we think global temperatures are going to be for the planet? Would I use this equation?
Yeah, you just take the Q as like energy from the sun, and then, we have the planet rotating, so that would be work and stuff.
So basically, we focus on this term, right? What is the total energy of the Earth over time by considering all the sources of heat in and out of the planet, right? So why does your car windshield frost over sometimes when other things don't? Does anyone know the answer to that?
Is it because the area of the car windshield is getting a lot colder and therefore becomes super saturated and condenses on the windshield?
The air around all the parts of the car are the same.
But the window is not as cold.
It's the inside of the car.
It's the orientation of the window, actually. It's oriented, and a lot of the window points to which direction? Outer space. So energy comes in the form of infrared. That heats it up. Energy leaves the window going out, and a lot of that energy goes out to outer space. Now, outer space is not contributing that much more energy to it. So your car windshield is radiating energy to a reservoir of outer space, which is at about 4 Kelvin, right? So when we're talking about energy balances, this is a very generally applicable thing. Now, for chemical processes, we generally like open, steady state. The reason why we like open and steady state is because we can find the optimum conditions to synthesize a chemical or perform some sort of a process, and then we keep it at those optimum conditions in perpetuity, right? We run those plants 24/7, only shutting them down maybe once every 6 months, once a year to swap out parts, change catalysts, clean process equipment, and things like that. Okay. So let's consider an open, steady process where I am mixing chemicals A and chemicals B. So we did this as an example of an adiabatic mixer, right? Where A and B may be at different temperatures. And this is the outlet of A and B mixed together. So if we assume a term called ideal mixing, right? And you guys did not cover mixing enthalpy in your Thermo 1 class, correct? Okay, good. If we assume ideal mixing, we can write, and I'm going to do this in terms of molar, right? So I'm differentiating here. This is mass, and this is kilojoules per kilogram. I'm going to do an underline here, or an underbar. This is going to be kilojoules per mole. Right, just to differentiate it, because in thermodynamics, everything depends on moles. So we can write that the enthalpy of a mixture of A and B is a weighted average. This is what we say when we assume ideal mixing. In addition, we can write that the specific volume is a weighted molar average of the individual specific volumes. So if I mix two chemicals together and they don't heat up or cool down, it's called an athermal solution. If I mix them and their density or specific volume doesn't change, if those two categories are satisfied, I have what we call an ideal mixture. Right? This is what we mean when I say ideal mixing. So if I mix two things together and it's not endothermic, where it feels colder, or exothermic, where it feels hotter, and the temperature that I mix is the same as the final temperature, right? That's called athermal. And that means that there is no enthalpy of mixing. We're going to talk about what that is in just a moment. If I mix the two things together and there's no change in density, if those two criteria are satisfied, we have what we call an ideal mixture. When we have an ideal mixture, we can show, let's say this is at Ta, this is at Tb. This is at.
So we're going to assume it's always ideal?
You will assume it's ideal unless you're given information for the non-ideality. So in general, yes, but I'll make it clear that this problem in this calculation is a non-ideal system. This is how you estimate it. So we're going to talk about how we cover that today. So if it's an ideal mixture, if I'm mixing two things at temperature A and temperature B, they could be the same, they could be different temperatures. I can model that as if A and B are two separate streams, right? And that's how we solved the adiabatic mixer problem before, right? So coming into the system, I have A coming at TA, I have B coming in at TB. Leaving the system, I have A at T and B at T. And so the adiabatic mixer energy balance ended up being the mass flow rate times delta HA is equal to the negative mass flow rate of B times delta HB, right? Do you guys remember this example we did? And we had to solve for what the temperature was by substituting in integral from T A to T, C sub P of A dt, m dot A equals negative m dot B, integral from T B to T, C sub B. Is this ringing a bell now? Some head nods, okay. In this problem, we assumed ideal mixing. Okay? In a real system, this is not the case. Fluid molecules don't necessarily get along with one another. So energy transitions happen. In the real system, I'll write out what the energy balance needs to look like. Okay? So in the real system, it's going to be 0 equals everything coming in. So it's going to be the mass flow rate of A, enthalpy of A, plus the mass flow rate of B times the enthalpy of B minus what's leaving the system. And I'm just going to call this AB, mass of AB mixed, enthalpy of AB. When I mix two streams together, the only time that I can consider their enthalpies to be separate is if I did ideal mixing. So if I were to do this in moles or that in, so this has to be in moles, but if I were to do this again in mole fractions and enthalpies per mole, you would see that if I substituted this into here, you could rearrange it to get something that looks like this. Okay? Work it out on your own if you don't trust me. But in a real system, the enthalpy is not just averaging or splitting the two apart. So what we would need is some experimental data. When I mix two fluids together, how does their energy change? Is heat given off or is heat taken in? If heat is given off, it's exothermic. If heat is taken in, it's endothermic. So how we can look at that is, let's say we set TA and TB equal to the same temperature. Okay? We can choose that as the reference state. And then we're looking at, is this term positive or negative, and that determines whether or not it's endothermic or exothermic. Right? So is the final solution enthalpy higher or lower? So in some circumstances, right, you can make the assumption here that it's ideal mixing, and usually that's a back of the envelope starting point. But in reality, I have to consider the outlet stream to be a new outlet stream with a complicated property setup. Okay. Did you guys cover entropy of mixing in your Thermo 1 class? Does anyone know what the entropy of mixing is for an ideal gas system? Does anyone remember the equation? But I can confirm it was covered, right? Okay. Does that look about right? We do have a, I think I have a, that's a negative sign here, I think, right? Yeah. Because natural log of a number less than 1 is always going to be negative, so it has to be positive. Okay. What are the properties of an ideal gas? Yeah. Perfect. So what happens if I put a mixture of ideal gases together? Do they know each other exists? No. So entropy will increase when I mix two things together because they don't spontaneously unmix. So if I have a mixture of A and B, so I'm going to call this the ideal or ideal gas mixing. Okay? In ideal gas mixing, it is totally random. A molecules don't know that other A molecules are there. B molecules don't know that other B molecules are there. And A molecules don't know that B molecules are there. Okay? Now, in a real system, the molecules know each other are there. So a really good example is sulfuric acid and water. Okay. And when we mix these together, is it endothermic or exothermic? Exothermic, right? So this is probably something that was talked about in chemistry courses. So let me see. I think I have it. I'm not good with my chemistry, but I think I have the, oh, here it is, the structure. So sulfuric acid looks like this. Okay? And water, of course, looks like this. So sulfuric acid has a bunch of lone pairs. Water has some lone pairs also. So what ends up happening is that in water, this is electronegative pointing this way. This is electropositive by the hydrogens. Same thing is occurring in sulfuric acid, where I have electronegative regions. And then as soon as this hydrogen goes away, right, SO4 2 minus, right, sulfate. So when I dissolve sulfuric acid into water, the molecules definitely know where each other are. And what it looks like is I have my sulfur, or my sulfate, okay, in solution, and the water molecules the positive regions where the hydrogen are attracted to the negative regions where there's the charge there. Is this random mixing? This concept is a good transition into our next and final sort of push of the class, which is going to be energy balances of reacting systems. This is not quite a chemical reaction, but it is pretty close, right? Because I'm ripping away a really easily removed proton that is then also going to be surrounded and solvated by the water molecules itself. Right? So there's a structure of how the water molecules organize around that proton, which is the source of acid and basidness. Okay? So, if we assume that positional mixing is totally random and that the fluid molecules don't interact with each other, or rather they interact with each other the same as they interact with themselves, we can assume ideal mixing. Anytime that we have order or structure in our fluid, we have a non-ideal fluid. Okay? So, to the first point about interactions. Water oil is 100 times C. Okay. Water. Molecular weight of 18, boiling point of 100 degrees C. Benzene, molecular weight of 80, boiling point of 80. Why is benzene so big, but yet boils at a lower temperature than water, which is a very, very small molecule? Yes?
Water is hydrogen bonding.
Water has hydrogen bonding. That's a generalization of the electrostatic force. Right? Water has what we call a permanent dipole. So did you guys go over the strength of bonds in your chemistry courses? What's the strongest bond?
Ionic.
Ionic. Then? Covalent. Then? Hydrogen bond, which is a generalization of which type of force?
London dispersion.
Permanent dipole. London dispersion force is which one? Strongest or weakest? Weakest. So what's in between permanent dipole and London dispersion? Dipole-induced dipole, right? One dipole induces a dipole in another molecule. That is the case with benzene. Benzene is not a polar molecule, but it is what we call a polarizable molecule. So benzene induces a dipole in itself, and that's why it is actually relatively cohesive together.
We don't actually have to know all that, right?
No. That's just for fun. But what you do have to know is under what circumstances can we assume ideal mixing and under what circumstances can we not assume ideal mixing. So, the ideal gas case is simple to understand. A doesn't know that A exists, B doesn't know that B exists, and A and B don't know that each other exists. Okay? There are 0 intermolecular interactions in an ideal gas system. In a real fluid system, okay, water interacts with other water molecules through a permanent dipole that is so strong that we give it a new name called a hydrogen bond. Right? The dipole is so big that we give it a special name, but it's really just a strong permanent dipole. Benzene interacts with each other through an induced dipole. It is a polarizable molecule. So benzene interacts with benzene through polarizability. Water interacts with water because of a permanent dipole. So when I try to mix benzene and water, do we think that they would mix well?
No.
They mix quite poorly because they have very different types of interactions. So, in an ideal mixture, I can have interactions, right? Let me do it this way here. When 2 molecules that are not ideal gases, but are ideal mixtures, okay? There's a distinction here. A will interact with A through, let's say, some energy function UAA. Okay? B will interact with B through some function we'll call UBB. B will interact with A through some function we'll call UAB. This will be an ideal mixture if UAA equals UBB, which is equal to UAB. So if the interactions between A and A, so in this case, let's say it's water, these are permanent dipole, very, very strong interactions. UBB, let's say, is benzene. This is an induced dipole. It'll have a certain interaction energy. And UAB would be the interactions between the two. How much does A like B? If they're all equal to the same, this will be an ideal mixture. Okay? Does anyone know how I could estimate the energy of UAA or UBB? Yeah. Perfect. It'll be closely related to the heat of vaporization. So imagine you reach into a liquid and you grab one molecule and you pull it out and move it away. That liquid is attracted to that molecule. And so when I pull it away, that's effectively the amount of energy it takes to vaporize the system. Now, vaporization is a little bit different because vaporization is you're pulling all of them away from everything, right? But it should be relatable. So fluids with similar heats of vaporization may have similar mixing properties. Solutions with similar critical points should have similar mixing properties, right? But this is the condition that has to be satisfied if it's an ideal mixture. So, do we expect water and benzene to be an ideal mixture?
No.
No. We should definitely not be, right? The reason why sulfuric acid here is so exothermic is because the energy that it takes to rip away the hydrogen, so remember there's a hydrogen here, the energy that it takes to rip this hydrogen away, right, that's going to be some positive. I have to pull that away. But then, when these water molecules attach to this negative electron there, I go to a very, very low energy state. Okay? So I'm breaking a high energy bond, and I'm forming a low energy structure or low energy bond. That is the case for an exothermic system. If I were to try and mix water and benzene, it would most likely be an endothermic system, because benzene and water don't like each other. So they have to steal energy from the kinetic energy of the system to rearrange to the configuration where water could try and be involved with benzene. All right. So that is a lot of words to sort of communicate the concept of non-ideal solutions. So how do we tackle this problem? For our purposes, the way we tackle this problem is experimental data. Okay? So if I'm going to mix, and I'll just do the water sulfuric acid again, into a system where we can put Q in and out. The energy balance will work out to be Q is equal to the delta H. Actually, let me get rid of that delta H. Well, I'll keep it in there because that's what we use for the nomenclature. This is going to be okay, final minus initial. So this is the enthalpy of sulfuric acid dissolved aqueous. This is their outlet stream, so H2SO4 aqueous. Of course, then there's going to be the water there. Minus the enthalpy of the water plus the enthalpy of the sulfuric acid. Okay? First, this will be ideal if Q is equal to 0. If Q is less than 0, this is exothermic. And that is because, I'm going to call all of this here H in. Question.
Yeah, I was going to say the Q isn't external in this case, right? It's being like generated by mixing it.
So this will be, let's say this is isothermal. So we have to either put energy in to keep it isothermal or take energy out to keep it isothermal. Okay, so if Q is less than 0, we generally know that means exothermic, right? It's a little bit confusing with the signs here a little bit, but this would be the case if the enthalpy in is greater than the enthalpy out. So this would correspond going from a high energy to low energy state or configuration. Okay? So in an exothermic system, we are going from water and sulfuric acid that are relatively higher energy states than when we have the solvated sulfuric acid. So the reason why it's exothermic is because the final energy state is at a really, really low energy level. So now I have all of this extra energy that has to go somewhere. So that it can either go into heating this solution up, so increasing the kinetic energy of the fluid, or I can pull it out of the system, right? So I drew the arrow Q going positive, so Q negative mean that heat is going this way. Is this too basic or too complicated? Am I losing people or are you bored? I don't have a good gauge of the room. Somewhere in the middle? Okay. The confusing part, to me at least, when we talk about endothermic versus exothermic systems, right? We think, okay, that I mix water and sulfuric acid together and then I touch the beaker and I go, ooh, that's hot. That's a high energy state. Right, does that make sense? But the confusing part is the reason why it's hot is because some of this energy here of the interactions between A and B, right, that gets substantially lowered. So I fed the system a lot of energy that is stored in the configuration of the molecules. Once the molecules rearrange, they're at a much lower energy state. So now I have all of this excess energy that didn't have anywhere to be before, and it says, oh, I'll just heat the fluid up, and that'll store the energy. And that's why it gets hot. So exothermic is going from high energy to low energy, so we have extra energy that needs to go somewhere. Yes?
So could we find those enthalpies by using the enthalpy formation of aqueous, the H2SO4 versus enthalpy formation of liquid H2SO4?
Yes, but I think that that math is backwards to how it's actually developed. So what you would actually do is mix these two things together in something called a calorimeter, right? So how a calorimeter works is I have a fluid that's contained in a little device that measures how much heat comes in and out of it, and then I have another fluid inside of a little ambule that's made of glass, and I break that, I allow them to mix, and then I measure how much energy goes in or out of the system to keep it isothermal. All right, so I use an electric heater or an electric cooler with a feedback loop, and I measure the current that I have to put into my electric heater to heat it up or cool it down, and then I can determine how much energy it took to keep this thing isothermal. That is called the delta H of mixing. Okay, so this here is all delta H of mixing. Yes?
So then are we going to be typically in a problem like this or typically going to be given the delta H mix?
You will, yes, you will be given a formula or more likely a chart that tells you what the delta H of mixing is. So the complication is knowing the definition and knowing what it communicates. So the delta H of mixing is I have enthalpies coming in, enthalpies coming out isothermally. Different charts will have different reference states, right? And so you'll see some more examples of this as we go on. But what we need to determine here is the enthalpy of the outlet stream if we were to do a problem like this one here of mixing. Okay? Generally speaking, we will assume that these are 0, right? Because we can choose the reference state. So that means if I need to determine what is the enthalpy of a mixed A-B stream, if this is done isothermally, then I look up what the heat of mixing is, and that is the enthalpy. Okay? So just to finish this off here, if Q is greater than 0, this is endothermic. That would mean that the enthalpy in is less than the enthalpy out. And this would be going from a low energy to a high energy. Okay? So if I took molecules that really liked each other, okay, they were in a really good, stable relationship, and then I mix them together with some other molecules that they don't get along with, they need some incentive to hang out together. This is a high energy state. So what they do is they say, I need a little extra energy, so I'm going to steal it from the kinetic thermal energy of the system, and that's how I can get to this stable energy configuration. So that would either lower the temperature of the solution, or I would have to put energy into it in order to keep it in that organization. Okay, on a scale of 1 to 10, conceptually, do we understand why this occurs? I got a couple 10s. I got 9. 9, okay. Okay, good. Mathematically, you'll have to struggle a little bit on the homework when we have these types of questions, but I think that's the better venue to learn it. Chemical reactions. How do we feel about chemical reactions compared to this concept here? Do you think chemical reactions are easier to understand or harder to understand? I got an easier vote. About the same. So let's think of it this way. In an ideal gas system, these gas molecules are zipping around everywhere. Okay? There's no correlation between A and B molecules. In water, are the water molecules totally randomly moving around? Does water have structure? Okay. In your chemistry classes, did you guys talk at all about solubility of different salts and coordination numbers maybe? Does that term ring a bell? What's a coordination number? Does anyone remember? It's how many water molecules surround a particular ion, right? So for sodium and chloride to be separated, they need to be surrounded by water molecules so they don't just stick back together. So the number of water molecules it takes to stabilize an ion is called a coordination number. That's exactly what we have here. Sulfuric acid has a coordination number. Now let's think of a chemical reaction, but instead of with molecules, with atoms. So if I have carbon and there are 4 hydrogens surrounding it that are bonded to it with a covalent bond, we have a new molecule, and that's called methane. Right? So chemical reactions are the same concept. If I have atoms coming together or molecules coming together and reacting to form new molecules, it would be exothermic if heat is being given off by the process and I kept it isothermal. That would be the same as saying that the enthalpy coming into the system is greater than the enthalpy coming out of the system. That would mean that I'm going from high energy bonds to low energy bonds. Likewise, if it's endothermic, my enthalpy coming in would be less than my enthalpy coming out. I would be going from low bonds to high energy bonds. So let's look at the combustion of methane because that's a really nice, easy example. Okay, and let's not forget that we still had time before energy balances in this class. 1 carbon, oxygen. Okay, there's 2 there. Let's not do the oxygens, let's do the hydrogens, 2. So I need 2 of these here. So now I have 1, 2, 3, 4. So I need 2 of those here. Okay. So in methane, is this an endothermic or an exothermic reaction? Right? It'd be really unpleasant if it was endothermic because this is where we get a very, very large fraction of our energy. So which of these bonds is high energy and which of these bonds is low energy?
The products would be low energy.
Products would be low. and the reactants would be high. So specifically, what chemical bonds are high energy? CH. Which ones are very low energy bonds? O2, I'm actually not 100% sure how strong it is relative to other ones. But the net balance, yeah. Well, so the OH I know is a very low energy bond, and I also know that the CO bond is a really low energy. But off the top of my head, I don't actually remember what the energy it is to split this apart is. Okay. So what makes something a high energy and a low energy bond? In our purposes, we don't actually need to know the underlying physics of it, right? We don't need to know the fancy chemistry associated with it. What I call high, someone else may call low, depending on the field that you're in. So when I say high, I mean it is high relative to the product that we care about, right? So the CH bond is a high energy bond relative to the OH and the CO bonds. But in terms of absolute scale, it's not too important. So what we're doing in a chemical reaction is the same thing as what we're doing in the mixing scenario. With classical thermodynamics, can I predict what the energy of this CH bond is and the OH bonds are? We cannot. We can't even estimate heat capacities. What chance do we have of estimating the energy of the underlying quantum mechanical processes that involve the covalent bonding? So what data do we use as chemical engineers to help figure out these types of problems?
The delta H formation.
Delta H of formation, but how is that obtained? Not quite empirical. We measure it experimentally, right? So what we're going to rely on is experimental data. Mixing, experimental data. Reactions, experimental data. Okay? So from here on out, we're going to transition into delta H with reacting systems. Basically until the end of class, we're going to talk about a lot of different strategies. And then we'll do a little bit on transient systems. So then basically redoing absolutely everything for the class, but instead of solving it where du dt equals 0 or dm dt equals 0, it is no longer equal to 0. And now we have an ordinary differential equation or a system of ordinary differential equations. Okay, so what I'll do is I'll just wrap up with a few bits of terminology associated with reacting systems, and then we'll pick up on it again on Wednesday. But I have said time and time and time again, the difficult part about energy balances is not the energy balance. It is determining the enthalpy values to put inside of that balance. It is choosing the reference state. It is finding the data that allows you to get from one state, unmixed water, to a second state, water mixed with sulfuric acid. Right? So we've got heating, that's the heat capacity. Right? I've got changing states, that's the heat of vaporization, or the heat of fusion if I'm going to a solid state. Now we're adding in changing the composition of the system, that's a delta H of mixing. And now we're adding in one other final one, which is the energy of changing chemical bonds. So the delta H of reaction is going to be equal to the stoichiometric summation of all the stoichiometric coefficients multiplied by their respective enthalpies. Now, if you want to get really complicated, This is further complicated by the fact that, let's say I had a chemical reaction occurring between the water and sulfuric acid system. I have to treat that as an entirely united system as well. So we're not going to do non-ideal reactions. We're only going to do ideal gas reactions. Okay, so we're going to keep it simple. So we're not going to mix the reactions with the non-ideality because that would be a very difficult task. Okay? So this is then going to be equal to, right, the final minus the initial state. So then we can break this up here into, well, we don't need to do that. This is pretty clear. Okay, so if I have an arbitrary reaction here of, let's say, A plus 2B goes to C plus D, and I say that the delta H of reaction here is equal to minus 100 kilojoules per mole. This week we will talk about how we get this delta H of reaction through the formations, but I just wanted to talk about, let's say you were given a reaction and given a delta H of reaction. Somebody measured it experimentally. Okay? We can estimate this, but we'll talk about that in a moment. What is the negative 100 kilojoules per mole? All right, so this is exothermic. Right? Is that per A, per B, per C, or per D? What is it? What is the mole? Is it moles of A? Is it moles of B? Is it moles of C? Or is it moles of D? Which mole is it? Yes?
You could group the moles together, so for every mole with one unit being 1A and 2B together, that's...
Exactly. And there's a concept that we talked about that encapsulates that idea perfectly, and that's the extent of reaction. So this mole here, right, is for extent. So the delta H of reaction is equal to minus 100 kilojoules per mole of A consumed, which is the same as minus 100 kilojoules per 2 moles of B formed, which is equal to minus 100 kilojoules per mole of C formed, and so on and so forth, right? Yep, you're right. Sorry. I blame the weather. So I'm trying to get the right equations on the board to help you out. Just put a few more definitions down, and then we can call it a day. So the number of moles of species I is the number of moles of species I initial plus the stoichiometric coefficient times by the extent of reaction, right? This is what we use to define our extent. Yes, question?
Why would it be positive 100 kilojoules for the mole C form?
So if I am creating a mole of C, I have to be consuming two B's and one A. So I can't independently create the C. So I would have to react these together, create the C and the D, and that whole process produces 100 kilojoules per mole coming out.
Okay.
So that's why, I couldn't make C without that whole process. So in order to break these bonds and form these bonds, the whole thing comes as a package.
Okay.
Yeah. All right, well, you know what? I will just wrap this up on Wednesday, revisit this. We'll talk about formation reactions and continue on with reacting systems. Okay.
Are you going to post homework 8 later?
I am going to post homework 8. Oh, and also for the project, I'm not sure what the deadline says on Canvas, but disregard that. I'll make sure that you have enough time to work on it. So that's just a holdover from previous years. So yes, project should be posted soon. Homeworks will be graded, regrades will be taken care of, homework aid will be posted. I got a busy week ahead of me.